Today we're going to be talking more about electrons. We're on the unit of electrons, and we're talking specifically today about that address, the electron configuration. We are going to be looking at three characteristics of electrons: how they're lazy, they're selfish, and they're antisocial. Now I've drawn, or Miss Adams has drawn a picture of a plane here, and I'm going to use this to demonstrate the lazy, selfish, and antisocial. Now imagine, for those of you who have flown alone, that you're on maybe like the small Alaska Airlines planes. They have 2 rows and 2 seats in each row, right? So there's an aisle in the middle, and there's 2 seats per row on either side of that aisle. So the first thing is, when you're getting onto a plane, where are you typically going to sit? If you're like most people, you're going to want to sit near the front, right? Because you're lazy, or because you just want to get off the plane first at the end of the flight. Where else are you going to sit? All right, we know that there's only 2 seats per row, so you can't fit more than you and another person in that row. So you're only going to have 2 of you sitting together. The last thing is, and that's being selfish, right? You're not letting anybody else in there. The last thing is, you're probably going to be a little antisocial, because we all are on a plane when we're traveling by ourselves. You're going to sit in a row that doesn't have anybody in it, typically, because you want to be by yourself. If there's no more room, eventually somebody's going to sit next to you. All right, so these are our same characteristics of electrons. They're lazy, selfish, and antisocial. According to the Aufbau principle, electrons being lazy means that they will fill the lowest energy levels first. Just like you sitting at the front of the plane, they're going to fill lower energy levels before they can go higher. They're also going to be selfish, according to the Pauli exclusion principle, which says that there can only be 2 electrons per orbital. Just like you can't have 3 people in your row of 2, electrons can only fit 2 electrons in each orbital. Lastly, according to Hund's rule, our electrons are antisocial. All right? So just like you don't want to sit by anybody if you don't have to, electrons are only going to double up in an orbital when they have to. They will remain 1 electron per orbital until it's completely necessary for them to double up. We're going to show you what this looks like in a second.
We do just want to remind you about how many electrons can fit into our different sublevels. Now remember, we have our first quantum number of n, which is the size, and that's our principal energy level. And then we have L, which are our sublevels of S, P, D, and F. So our S orbitals are going to have there's only going to be 1 shape for that.
Remember, our S shape is a sphere.
And then that is going to be able to hold a total of 2 electrons because there's only 1 orbital. For P, we are going to have 3 different orientations. So we will have 3 orbitals, and each of those 3 will be able to hold electrons. So that is a total of 6 electrons. D, 5 different orbitals. Each of those will be able to hold a total. Each of those will hold 2, so 5 times 2 is 10 electrons. And then F, 7 orbitals. Remember, those are really complex looking, and so we don't have a good physical diagram of it. But they will each hold 2 electrons, so we have a total of 14. Now, we're going to use an Aufbau diagram to kind of synthesize all of this information and what you learned in the POGL to write out and fill in the electron configuration, the filling order, essentially.
All right, so the first thing is we're going to start at the bottom of our Aufbau diagram. This is Aufbau's rule. We start at the lowest energy level first. All right, after that, we're going to make sure that there's only 1 electron per line before they double up. This is Hund's rule. And arrows on the same line are going to go in different directions. Remember that I said in the last video, 1 electron will spin clockwise, 1 will spin counterclockwise. They do not go the same direction. All right, so that's our electron spin as part of our quantum numbers, the m sub s.
Okay, so we're going to do 3 different examples for you right now, and I know this periodic table is small, but I promise it's useful. We're first going to do oxygen, then fluorine, and then neon.
They're right next to each other.
They are right next to each other. So oxygen has a total of 8 electrons, so we are going to fill it like so.
1 up, 1 down?
1 down, 1 up, and then 1 down, and that's all that can fit in our first energy level.
Then we're going up to the next energy level to 2s. 1 up, 1 down. We're at 4 electrons.
Okay.
Notice that these are by how much energy they have too. So you'll see that 2p is slightly before 3s. So now we're going to go to 2p.
And remember, this is where our other rules come into play. Although we have 8, so we have 2, 4, 5, 6, 7, and they're all only going to they're not going to double up until they have to. And now this last one has no choice but to double up, and so we draw an arrow in the opposite direction.
For that first line.
Okay, so
There's
oxygen has 8 electrons. Fluorine has 9, so it would have one more electron. That would exactly like
doubling
that.
up now that it has
doubling
to.
up there, and then neon would have 10. Okay.
Perfect.
Do we want to add anything else?
Nope. I think that's good. All right. Now we're going to get on to representing electrons in an atom using electron configurations and orbital notations. I'll put this up if you talk.
Okay. So, electron configuration, this is what you saw in the end of the POGL, and it's basically an electron's address in an atom. And we're going to talk about what that means and how we can determine this, and you can write it out using the periodic table. I do just want to let you guys know that these energy levels right here, the 3s and 3p are going to have they're the highest energy levels, and those are always our outermost electrons, and so they come at the end of our electron configuration, and they're the last ones to fill in this case.
All right, so if this is the electron configuration, just like you saw in the POGLs, we're going to draw the orbital notation for that. Now, this is just like the alphabet diagram, but sideways, so it's going to follow the same rules. We have 1s2, so we have one arrow up, one down. 2s2, one up, one down.
2p6,
one up, one up, one up, one down, one down, one down.
3s2,
one up, one down.
and 3p3.
One up, one up, one up. So that would be our orbital notation for phosphorus, following that electron configuration. Now, how many energy levels do we have here? If we look, we have energy level 1, 2, and 3. We have 3 energy levels. How many sublevels do we have? Well, each one of these is a sublevel. So there's 1, here's 2, 2p makes 3, 3s makes 4, and 3p makes 5 sublevels here. How many orbitals do you see? Each orbital holds 2 electrons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So each orbital can hold up to 2 electrons. And how many electrons do we have here? We can count them, right? 2, 4, 6, 8, 10, 12, 13, 14, 15. We can also count them on the electron configuration by looking at those, the upper numbers.
2, 4, 10, 11, 12, 13, 14, 15.
Perfect.
Double checking.
All right, so we are going to look at the periodic table and how we can actually use the periodic table to help us write our electron configurations, which we then use for our orbital notation.
So first we're just going to talk about the arrangement of this and how we're going to use it, and then I'm going to show you how to write some of the examples right here. First of all, these are our principal energy levels, and you'll see they increase as you go down the periodic table and as we get more electrons. Okay, so these are our principal energy levels. You should write that down even though we didn't. Then we have what we call blocks, and that is our different actual sublevels. And we have the S block, which is S block, these guys, plus our helium, because he's special. And then we have the P block, which is all of these guys over here. So this is kind of this is the division. This is the division. Then we have the D block. And then we have the F block. And we're going to talk about filling order right now and explain everything, but I do just want to tell you that when we go and we look at the actual energy level, we want to tell you that D actually drops down 1 energy level and F drops down 2 energy levels. And I'll explain that more as I am doing the electron configuration for a more complicated atom. So I'm going to first start with magnesium, which is located right here on the periodic table. And all I do is I start with 1s and I read all the way across, and I fill my electrons in that order. So, do you want to print?
So you go with the electron configuration. I'm holding this a little closer.
Oh, will
All right.
you arrow though a little bit? So magnesium is going to start with 1S, where I get the, you're pointing, okay. 1S, and then it's going to have 1 and 2, so it will have 2, and then it's going to be 2S2.
Now we're here.
2P6.
Takes us to neon.
3S2.
And that's it.
Sorry.
There's magnesium.
And there is magnesium. Great. And remember, these are my outermost electrons in my S level.
So if I'm going to do the orbital notation for that, it's going to look like this. 1s, 2, 2s, 2, 2p, 6. I don't know why I didn't have another one here. 3s, 2.
Great. Okay. And then for aluminum you can see is just 1 over. So we're actually going to have the same electron configuration, 2p6, 3s2, all the way
magnesium.
to magnesium. And then we have one more electron. And so it's going to be in my 3p orbital, and it's going to be 3p1.
Right? Orbital notation, it's going to look the same. I don't know why I didn't write enough here. 1 up, 1 up, 1 up, 1 down, 1 down, 1 down, up, down, and our 3p will have 1 electron.
Silicone, again, is just the same. I'm just going 1 additional.
Right here.
So I would have 1s2, 2s2, 2p6, 3s2, 3p, not 1 anymore, but 2.
That's 1 more electron. And again, up, down, up, down, up, 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 down, 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 up, down. And we have 3p, 1 up, and 1 up. So this third orbital here is empty.
Okay. Lastly, we are going to do zinc and then plutonium. Now, zinc is going to help us to demonstrate what happens when we do D and F orbitals. So really, I'm going to start out, and I'm going to have 1s2.
Takes us to helium.
2s2.
To beryllium.
2p6.
To neon.
3s2.
To magnesium.
3p6.
To argon.
4s2.
To calcium.
And then 3, because remember my 3 actually my D actually drops down 1 energy level. That's what we need. So this entire
block right here drops down 1.
3D, and how many do I have? I have to count all the way over, and it's going to be a total of 10. Okay, so this is my demonstration of my dropping down. Okay, I'm also going to do we have time?
Yeah, hurry.
Okay, I'm also going to do platinum for you. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 because it drops down 1, and that's not right.
Yeah, that's right.
No, F.
4s2, 3d10.
Oh, you're right. Sorry. 3d10. We're not there yet. Where am I? 4D.
4p.
4p. Oh my god.
You're good.
4p6.
We're at krypton.
3. I can't say the periodic table.
5s2.
5s2.
We're at 4d.
4. This is where I wanted to be. 4d. 4d10. And then 3.
And then 5p6.
5p6.
We're near the end. Now we're at 1, 2, 3, 4.
Where am I at?
6s2.
6s2.
We're going to drop or fall down here to the F. That's 2 energy levels we're falling. So this is going to be 4F.
F.
14.
14, because I have a total of 14. Right. And then
D only drops 1, so this is actually 5D.
5D.
Over to 8.
8. Sorry. I don't know why I jumped ahead. All right. Okay. I know that's it. Really long. Okay.